Extremal 4. Functional integral 0 to 1 y square plus y dash square dx, where boundary conditions are given by y of 0 equals 0 and y of 1 equals 1. We have capital F equals y square plus y dash square. Here we have dou f by dou y, that is fy equals 2y, taking partial derivative of capital F with respect to y, treating y dash as constant. Similarly, fy dash, which is partial derivative of capital F with respect to y dash, treating y as a constant, is obtained as 2 times y dash. By Euler's equation, we have fy minus d by dx of fy dash equals 0. That is 2y minus d by dx of 2y dash equals 0. 2 can be taken outside and we have 2 times y minus y double dash equals 0. This is because d by dx of y dash is y double dash. When you divide both sides of this equation using 2, it becomes y minus y double dash equals 0. When you multiply this equation throughout using a negative sign, or you multiply the complete equation using negative 1, you get y double dash minus y equals 0. We have the auxiliary equation corresponding to this equation is obtained as m square minus 1 equals 0. We are going to find the value of y, or which is the solution of this particular differential equation. And by auxiliary equation m square minus 1 equals 0, we get m equals plus minus 1 are the values, and we have whenever m equals plus minus 1, the solution is y equals c1 cos hx plus c2 sin hx. Now we will use the boundary conditions. We have y of 0 equals 0, from where we have x equals 0 and y equals 0. When substituted in the expression y equals c1 cos hx plus c2 sin hx, we will get 0 equals c1 cos h0 plus c2 sin h0. We have sin h0 equals 0 and cos h0 equals 1. Therefore we have c1 times 1 equals 0, from where we have c1 equals 0. Using the second boundary conditions, y of 1 equals 1, we have x equals 1 and y equals 1 to be substituted in the expression y equals c1 cos hx plus c2 sin hx. We have 1 equals c1 cos h1 plus c2 sin h1. We have already found c1 equals 0, thus we have 1 equals c2 sin h1. From this equation 1 equals c2 sin h1, we get c2 equals 1 by sin h1. Therefore, we have the required extremal obtained as y equals c1 cos hx plus c2 sin hx. Now, we will replace c1 by 0 and c2 by 1 by sin h1, so that we have required extremal y equals sin hx upon sin h1 by substituting c2 equals 1 by sin h1.